today we will discuss a different case of asymptotic estimate in a complex plane. Namely, we again consider Laplace type integral taking along the contour in some complex along some contour in a complex plane. But this time our f of x function doesn't have saddles in a complex plane. The typical situation is when we deal with the contour which is semi-infinite. This is one possible situation, or quite typical situation, either Hankel type contour. So we have a branch point somewhere, the branch cut, the branch cut is directed, for example, in some direction. Generally, it's a curve, and the contour is a Hankel type contour. So how do we build the asymptotic in this case? Well, to understand what is happening, let's actually make a suitable change of variables. So this is, of course, the complex plane of complex variable x. And let's call this initial point here x naught, and here x naught again. Then the suitable change of variables is as follows. Well, let's denote this f of x naught number as tau naught. Naturally, that kind of change performs a conformal mapping from complex plane x to complex plane t. If x equals to x naught, then t is equal to 0. So after this conformal mapping, the contour is changed accordingly. And let's address probably the most typical case is when we deal with Hankel type contour. And because after the discussion is over, you will realize how to perform the asymptotic estimate for a simpler contour, which is here. Right, so here is our new complex plane. And the branch point is mapped onto t equals 0. The branch cut say, of course, it will change its direction, and now it will start in the downward direction, for example. And the contour will change accordingly. Now let's see what's going to happen with the integral itself. F of x is now equal to tau plus tau naught, and x is f minus 1 of tau plus tau naught. And let's switch to this new variable tau. So dx is, of course, f minus 1 prime d tau, and function g of x is turned into the function of g of tau. So after this change, the integral is simplified and becomes the following expression. So generally, the simplification, in particular, it addresses the exponent form. Now the exponent is particularly simple. It's just lambda tau plus lambda f of x naught. And here we have g of f minus 1 of tau plus tau naught times f minus 1 prime d tau. And let's call this function h of tau. So now we have a simplified integral, and with particular suitable exponent. Now it's just lambda tau. We can factor out lambda f of x naught and put it in front of our integral. And let's call this contour now gamma prime. Right. And since we have the simpler exponential, let's analyze how the asymptotic is built. So lambda, for concreteness, lambda is supposed to be positive and large. So the steepest descent direction for the exponent is simply, well, let's just, so it's a imaginary part of lambda tau is constant line. But we realize, of course, that the crucial point for the whole integral is the vicinity of this tau equals to 0 point, the origin. Why? Because it's the point where the exponential is maximum. Well, of course, there are other points where exponential is even greater, but the general slope of the real part of the exponent function, it's a downward slope. So it's like a plane inclined in this direction. And for example, we could deform the contour like this, where the exponential function is great. But since there is no branch cut here, these contribution to the integral, they will cancel each other when we go to the right and return from the right to the left. So it is the vicinity of this point which makes the essential contribution. And at point t equals 0, the imaginary part, the whole function, the whole exponent function is 0, so the imaginary part is 0. And as a result, the steepest descent line is this. So unsurprisingly, it's this negative tau direction. And accordingly, the contour should be deformed in such a way that it passes, so it arrives at this branch point along the steepest descent direction and leaves it in the same direction. Well, at least for the upper bank part of the contour, there is no problem to deform it in the steepest descent direction. We just rotate it slightly like that, and here it is. Right, that's the steepest descent direction, and we just deform the contour like that. However, with the lower part of the contour, there is a problem. Why? Because the position of the branch cut forbids the contour to be deformed into this negative direction line. So what are we supposed to do? Well, fortunately, we understand that so there is a branch cut. That means that this g function is a multi-valued function, and so we should see this function as the function defined on on a set of Riemann sheets, and this branch cut is in fact the connection between the upper Riemann sheet and the lower Riemann sheet. So in fact, we can cross the branch cut, and the contour can cross it, but the continuation of the contour will belong to the lower branch cut or upper branch cut, depending on the situation of the second Riemann sheet, which is, for example, if it's below, then it's below the upper Riemann sheet, which is depicted on the blackboard. So let me show you with the visualization of the situation on my laptop. So that's the Riemann surface, the typical Riemann surface of the g of tau function. And here is the position of the branch cut. And this is the deformation of the contour, which basically perform the trick which we just discussed. Like that. So here we go. Now let's actually compute the integral and find the final explicit expression for the asymptotic series for this integral.